Memory management. Memory management is a critical function of an operating system that handles the allocation and deallocation of memory to various processes. Think of it as a traffic controller for memory distribution, ensuring safety and efficiency. It ensures efficient use of RAM while maintaining system stability. In computing, memory management is all about managing system resources, especially main memory. This management involves keeping track of each byte in a computer's memory and deciding which process gets how much memory and for how long. When multiple programs run simultaneously, the OS ensures each process gets the memory it needs without interfering with others. It also reclaims memory when a process is terminated. Types of memory. There are two main types of memory involved in memory management, namely primary memory and secondary memory. RAM is fast and volatile, meaning data is lost when power is off. RAM allows fast access to data for currently running programs, while secondary memory provides the space for long-term data storage. Secondary memory, like hard drives or SSDs, is used for long-term storage and can also be used to supplement RAM through techniques like virtual memory. When RAM is full, the operating system uses a portion of the secondary storage as an extension of RAM. This is known as virtual memory, which helps the system run larger applications even with limited physical RAM. Memory allocation techniques. Memory allocation involves assigning memory to programs and processes efficiently. There are several techniques for allocating memory, each with its own advantages and limitations. Broadly, memory allocation can be classified into two levels: operating system level allocation and program level. At the OS level, the focus is on how memory is assigned to processes. At the program level, it's about how variables and data structures are handled during program execution. Let's break them down one by one. Operating system level memory allocation consists of two major types: contiguous and non-contiguous allocation. Contiguous allocation is one of the earliest memory allocation techniques. In contiguous allocation, each process is given a single, continuous block of memory. It's simple and fast but leads to problems like internal and external fragmentation. Fragmentation refers to the inefficient use of memory that leads to unusable space. Internal fragmentation happens when memory is allocated in fixed-sized blocks and a process doesn't fully use the entire allocated space. The leftover space is wasted inside the allocated block. External fragmentation occurs when free memory is split into small blocks scattered throughout the system. While the total free memory might be enough, it isn't contiguous, making it difficult to allocate to new processes. For example, if memory is divided into fixed partitions, some of them may remain underutilized. In non-contiguous allocation, memory is assigned in blocks that can be scattered across the system. This approach improves utilization and flexibility. Key techniques include paging and segmentation. Non-contiguous allocation solves many of the fragmentation problems. Paging divides memory and processes into equal-sized pages and frames, making allocation more efficient. Segmentation, on the other hand, aligns more with the logical divisions in a program, like functions and data. Paged segmentation combines the best of both worlds for more efficient and logical memory handling. At the program level, we classify memory allocation as either static or dynamic. In static allocation, memory is allocated during compile time. It is fixed and cannot be resized during execution. It hence lacks flexibility. Since memory is reserved before the program runs, static memory allocation is predictable and fast. Dynamic memory allocation allows memory to be assigned at runtime, giving the program more flexibility. It is useful when memory needs are not known in advance. Dynamic allocation gives us control over memory use during execution. It's ideal when working with data structures like linked lists or trees that grow or shrink as the program runs. However, it requires careful handling to avoid issues like memory leaks or dangling pointers. Languages like Python and Java manage this more safely using garbage collection. Why do we need memory allocation? As we know, memory is limited, so allocating just enough memory to each process helps prevent waste and ensures smooth operation and hence uses resources efficiently. Memory allocation helps with process isolation, meaning each program runs in its own memory space. This prevents them from interfering with or accessing one another's data. Allocation allows several programs to run at the same time by distributing memory among them fairly. Programs don't always need the same amount of memory. Dynamic allocation adjusts memory use during runtime. Memory allocation enforces boundaries, ensuring user data is protected and systems remain secure. Lastly, proper memory allocation minimizes fragmentation and delays, making the system faster and more reliable. To summarize, memory management is a core function of the operating system responsible for allocating, tracking, and optimizing system memory. It ensures that multiple processes can run efficiently without interfering with each other. Without it, running multiple programs at once would result in data overlap, system crashes, and security breaches. Techniques like contiguous allocation, paging, segmentation, and virtual memory are employed to manage memory effectively. The system also enforces protection mechanisms to prevent memory access violations. Issues like fragmentation are addressed using various strategies, and in higher-level languages, garbage collection automatically reclaims unused memory. Overall, efficient memory management ensures stability, performance, and security in computing systems.